Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Computer Applications of Congruences, a Gentle Introduction. As always, please be an attentive learner as you watch this video. By way of introduction, congruences have many applications to discrete mathematics, computer science, and many other disciplines. We will introduce three applications in this section and a major one in the next section. We're going to talk about in this section the use of congruences to assign memory locations to computer files, the generation of pseudorandom numbers, and check digits for error detection, and also these are used for error correction. Okay, so let's begin. Suppose the customer identification number is 10 digits long. To retrieve customer files quickly, we do not want to assign a memory location to a customer record using a 10-digit identification number. Instead, we want to use a smaller integer associated with this identification number. This can be done using what is known as a hashing function. In this section, we will show how to use modular arithmetic to do hashing. Constructing sequences of random numbers is important for randomized algorithms, for simulations, and for many other purposes. Constructing a sequence of truly random numbers is extremely difficult and perhaps impossible because any method for generating what are supposed to be random numbers may generate numbers with hidden patterns. As a consequence, methods have been developed for finding sequences of numbers that have many desirable properties of random numbers and can be used for various purposes in place of random numbers. And we're going to call these things pseudo-random numbers. And we can use, and congruences often are used, to generate such sequences. The advantage is that the pseudo-random numbers are constructed quickly, and the disadvantage is they may have hidden patterns. Congruences are also used to produce check digits for identification numbers of various kinds, such as code numbers used to identify retail products, numbers used to identify books, airline tickets, and so forth. We will explain how to construct check digits using congruences for a variety of certain types of mathematical identification numbers. We will show that these check digits can be used to detect certain kinds of common errors when the identification numbers are printed. Let's begin then with hashing functions. The central computer at an insurance company, as an example, let's talk about this, maintains records for each of its customers. How can memory locations be assigned so that the customer records can be retrieved quickly? The solution to this problem is to use a suitably chosen hashing functions. So records are identified using a key, which uniquely identifies each customer record. For instance, customer records are often identified using Social Security number of the customer as the key. A hashing function h assigns a memory location h of k to the record that has k as its key. In practice, many hashing functions are used. One of the most common is the hashing function h of k equal k modulo m, where m is the number of available memory locations for the customer records. Hashing functions should be easily evaluated so the files can be quickly located. The hashing function h of k equal k mod m meets this requirement. So to find hk, we need only compute the remainder when k is divided by m. Furthermore, the hashing function should be onto so that all memory locations are possible. And this is also an onto function because for every k in mod m, you certainly can find something that maps to it. In fact, you can find many things, so it is not one-to-one. So here's a problem that we'll do, and instead of having delays here, I'm just giving you the problem, but you should really pause here. So the first problem is find the memory location assigned to the hashing function h of k equal k mod 111 to the records of two customers, one with Social Security number, this first number, and the other one with Social Security number, the second number. You know what to do. and let's see how you did. The record of the customer with Social Security number first is assigned to 14 because when you divide this number by 111, your remainder is 14. And similarly, this other Social Security number, when you divide by 111, you get 65. So those are the locations in memory that are assigned to those two customer records. Now, because a hashing function is not one-to-one, we talked about that, because there are more possible keys than memory locations, more than one file may be assigned to a memory location. When this happens, we say a collision occurs. One way to resolve a collision is to assign the first free location following the occupied memory location assigned by the hashing function. So here's another example. After making the assignments of the records that we had up here, those two, we want to assign a memory location to the record of another customer with this Social Security number. You know what to do. Now, first note that the hashing function maps this new 1 to 14, because when you change this to mod 14, you get, to mod 111 rather, you get 14. However, this location is already located the previous record, but because the memory location 15 is not used, we assign that to the to this number, and that will be the location for this. So you do have to deal with collisions when you doing this form of memory management. Now, in this example, we used a linear probing function. That is, we just went to the very next one. So hk of I is going to be hk plus I mod m to look for free memory locations, where I will run from 0, that's if it works the first time, to m-1 if you have to look for all of them. And if you look at all of these, then you say I've used up all my memory locations. But there are many other ways to resolve collisions, and these are discussed in detailed references, and you should realize that someday you might end up studying this even more seriously. Our next example deals with pseudo-random numbers. Randomly chosen numbers are often needed for computer simulations. Different methods have been devised for generating numbers that have properties of randomly chosen numbers, and these are called pseudorandom numbers. Now, the most commonly used procedure for generating pseudorandom numbers is called the linear congruential method. We choose 4 integers: a modulus m, a multiplier a, an increment c, and a seed x0. This is the seed of your random numbers, where a is between 2 and m, c is between 0 and m, and the seed is between 0 and m. So we generate a sequence of pseudo-random numbers x sub n, where n goes from 0, where x sub n ends up being between 0 and m for all n, successively by using the recursively defined function x sub n plus 1 is equal to, we calculate a times x sub n plus c, and we compute this mod m. And that is a recursive function that we've talked about previously. Many computer experiments do require you generate a bunch of pseudo-random numbers between 0 and 1. If we have to do that, what we will do is divide each of the numbers generated by the linear congruential generator by the modulus. That is, we would take xn divided by m. So let's look at an example. We want to find a sequence of pseudo-random numbers generated by the linear congruential method with modulus m equal 9, multiplier a equals 7, increment c equal 4, and the seed x0 equal 3. And if you change the seed, you change the sequence. You know what to do? Let's see how you did. Okay, so we will compute x1. x0 was the seed, so we'll compute x1, x2, and so on and so forth. So you see x1, I take 7, x0 plus 4, mod n. And I do the calculation, and I get 7 for that. Now x2 is, doing the calculation again, is 8, x3. And notice that each of these depends on the one immediately before. And we'll go up to x9. Because x9 equals x0, and because each term depends only on the previous term, this sequence is generated. Now notice that the sequence that is generated is we start with the seed 3, then we go 7, 8, 6, 1, so on and so forth. This sequence contains 9 different numbers before it repeats because of the modulus. And clearly we will use moduli that are much larger, but the programming will work exactly this way. Most computers do use this approach to generate pseudorandom numbers. And in fact, often they will take C to be 0, and that's called a pure multiplicative generator. To give you an idea of the size of these numbers, though, pure multiplicative generators often have modulus 2 raised to the 31 minus 1, an enormous number, with multiply 7 to the 5, which is 16,807, is widely used. With these values, it can be shown that this will generate a whole bunch of numbers before repetition begins, and so this is often sufficient number of random numbers or pseudo-random numbers to generate. These have been used for many tasks, but unfortunately that there are some properties that it doesn't do. So you want to be careful, and there are very sophisticated ways that can generate better functions using for large simulations. But if you checked into the details of Excel or maybe Python, you can find out what they actually use for here for these pseudo-random numbers, and a very important application. Let's move on to the application of check digits. Congruences are used to check for errors in a digital stream, because there can be transmission errors, there can be coding errors, there can be input errors, so on and so forth. So a common technique for detecting errors in such strings is to add an extra digit at the end of the string. This final digit, or check digit, is calculated using a particular function. Then, to determine whether a digit string is correct, a check is made to see whether this final digit has the correct value. And this might not be foolproof, but it will pick up many errors. We begin with an application of this idea for checking the correctness of bit strings. This is called parity bit checks. So digital information is represented by the bit string, but is split into blocks of a specified size. Before each block is stored or transmitted, an extra bit called a parity check bit is appended to each block. The parity check bit x of n plus 1 for the string going from x1 to xn is defined by, and we just add these up and we convert this to mod 2. So either this is going to be even or odd, so this check bit will either be 0 or 1. It follows if this is 0 if you have an even number of 1 bits, and it is 1 if there's an odd number in there. So if we examine a string that includes a parity check bit, but we know there's an error if the parity of the check bit is wrong based on the other, there's an error somewhere. However, when the parity check bit is correct, there still may be an error because there actually could be more than one error. A parity check can detect an odd number of errors in the previous bits, but not an even number of errors, and you can think through that. Okay, so here's the kind of problem that I could ask here. So, think about this. Suppose we receive a transmission of the bit streams, this one, and later on this one, each ending with a parity check bit. This one is a 1 and that one is a 0. Should we accept these bit strings as correct? Okay, let's see how you did. So we do use a parity check bit, and so because here we find that this was congruent to 1 mod 2. The parity check bit is correct, and so that means that we should think that that's correct. But we conclude the first string has been submitted correctly, and the second string is rejected. Check bits using congruences are used extensively to verify the correctness of these. And in fact, we will look at a couple of examples, those of ISB codes and universal product codes that do this. And these things are used for money orders, airline tickets, identification numbers for periodicals, and so on and so forth, and even for driver's license and other credit card numbers. And so this is a very, very, very important application of these congruences. Let's look at what we do for UPC. So we have a universal product code, and it has 12 decimal digits. The first digit identifies the product category, the next 5 the manufacturer, the following 5 identify the product, and the last is a check digit. And this is the congruence that is used. So you take 3 times x1 plus x2 plus 3 times x3 plus x4, and you see every odd one we multiply by 3 as we go through, and we consider, is this congruent? Mod 10. So the check digit is determined by this congruence, and so the check digit is going to be a number between if it's congruent to 0, that means we think it's correct, and otherwise, if it's not congruent to 0, we think there is an error. Okay, so suppose the first 11 digits of a UPC code was this one. What is the check digit? And then the second one we ask, is this a valid UPC code? Okay, so when we insert these numbers into the congruence, and again, you'd write a program. This is hard to do by hand, but this gives you the calculation that is congruent to 0 mod 10. So we find that it is congruent, and therefore it follows that the check digit is 2. Okay, because all of this is we have to have 2, so it's congruent to 0. We're forcing the whole thing to be congruent to 0. And now if we wanted to check this one, where we do have the check digit already there, is valid, we insert it into those and we check to see if it's congruent to 0. Well, we get 4, which is not congruent to 0. Therefore, this is not a valid code. There was an error somehow. ISBN codes are codes that identify books, and now these days we have ISBN 13 codes as well, so this has been expanded. We're just talking about ISBN 10 here. Okay, so an ISBN 10 consists of blocks identifying the language, the publisher, and the book assigned to the book by its publishing company, and finally a check digit is added, either a digit or a letter, X, and X is used to represent 10, because these will be 0 through 9. This check digit is selected so that X10 is congruent to, you add up I equal 1 through 9, I times xi mod 11, or equivalently, and this we're just doing a little bit of a shift. If I add up all 10, it's congruent to 0 mod 11. And so I could ask you a question about the first 9 digits of an ISBN 10 number of the 6th edition of this book are this. What is the check digit? And I could also ask you, is this a valid ISBN number? And you know what to do. Let's see how you did. Okay, so here you can go through using the algorithm and you can check and find that X10 is equal to 2. So that is the check digit. To see if this is valid, what you do is you see, is this summation I equal 1 to 10, I times xi congruent to 0 mod 11? That is it divisible with 0 remainder when you divide by 11? So when we do this, we find out that we get 2. That's not congruent to 0 mod 11. Hence, that is not a valid ISBN 10 number. Now, several kinds of errors often arise in identification numbers. We can have a single error. We can have multiple errors, and even a very common error is a transposition error, which occurs when 2 digits are accidentally interchanged. For each type of identification number, including a check digit, we would like to be able to detect these common types of errors, as well as other type of errors. So we'll investigate whether the check digit for ISBNs can detect single errors and transposition errors. And so let's talk a little bit about that. So suppose that X1, X2, X10 is a valid ISBN, and so that's going to be congruent to 0 mod 10. So we can detect a single error and a transposition error when we include the possibility that one of the 2 digits is the check digit X representing 10. So suppose this ISBN is printed with a single error. Then if there is a single error, then for some some integer j, y sub I equals x sub I for I not equal to k, and it is a different number for the x sub j and y sub j. Therefore, that a is equal to y sub j minus xj is the error in the ith place. So if you do that, you're not going to get 0. And similarly, you can find that if you transpose, do a transposition, that also you will detect the error. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all on this together. May God bless you all.